Hi, I'm Chris, and in this video I'm going to begin the process of explaining how to build an 11-bit by 11-bit multiply circuit. However, before building a multiply circuit, it's necessary for you to know how to build a circuit which performs binary addition. I expect that if you're following this series, you probably already know how to build a simple adder circuit. Still, it's possible that some of you are starting from scratch, so this video will cover a simple ripple carry adder. Up until this point, I've been relying on the Verilog compiler to generate integer addition, multiplication, and comparison circuits for me automatically. One of the reasons I started this project was to understand how to build floating point hardware which would perform the computations as fast as possible. Relying on the Verilog compiler doesn't give me any insight into how to make these circuits fast. By developing my own versions of these circuits rather than relying on the Verilog compiler, I hope to achieve that goal. In the process of building the 11-bit by 11-bit multiply circuit, I'm going to start by building a circuit which is simple and correct before considering how to make the circuit fast. Again, my experience working with computers has primarily been as a software engineer, and all properly trained software engineers should be well versed in the writings of Donald Knuth, who admonished us that premature optimization is the root of all evil. With that in mind, we can now begin. Adding 2 bits is fairly straightforward. These are the 4 possibilities for adding 2 single-bit quantities. Notice that in the 4th case, we end up with a sum which is 2 bits wide. The leftmost bit becomes a carry bit, which gets added to the next more significant column. This is the truth table for adding 2 single-bit quantities, where A and B are the inputs, and S and C are the sum and carry bits respectively. Now that we know how to add 2 1-bit quantities, let's take a look at adding 2 4-bit numbers. These numbers are the binary versions of the decimal numbers 3 and 5. We start by adding the 2 rightmost bits. These bits are both 1, so the sum is 0, and the carry bit is 1, which looks like this. Now we add the next column to the left. The carry bit is part of the addition, so we're adding 1 plus 1 plus 0, which gives us a sum of 0, and the carry bit is 1, which brings us here. Adding the next column is 1 plus 0 plus 1, so the sum is 0, and the carry bit is 1. Finally, we add the last column, which is 1 plus 0 plus 0, so our sum is 1, and the carry bit is 0. Notice that for the last 3 columns, we have to add 3 bits, so we need a different set of equations from what we use for the rightmost column. The truth table for adding 2 1-bit quantities only had a carry-out bit. The truth table for adding 3 bits adds a carry-in bit, and this is the truth table for the last 3 columns, where C sub n is the carry bit from the previous column, A and B are the remaining inputs, S is the sum, and C sub out is the carry bit to be added to the next more significant column. This truth table describes a full adder. The previous truth table describes a half adder. Logically, a full adder is 2 half adders plus an OR gate. For more details about the logic equations for adding binary integers, see the video in the link which appears on your screen now. So, if we have 2 4-bit vectors, A and B, as input, and I wish to perform addition, how do I write the logic equations? This is one possible solution. Note that the logic equation for the least significant column is different from the logic for the remaining columns. I could write the addition module differently by creating a half adder module and a full adder module. The code for the half adder module might look like this. As mentioned previously, I can build a full adder out of 2 half adders and an OR gate. I could also write the full adder like this. Using the half adder and full adder modules, I can rewrite the 4-bit adder module like this. Now that we can build a circuit to add binary numbers, we can talk about how to do multiplication. Starting with something simple, let's look at 5 times 3. One way we can perform this computation is to add 5 3 times. 3 plus 3 plus 3 plus 3 plus 3 equals 15. If I were going to write a program to perform multiplication using this technique, it might look something like this. In this code, it's my intention that unsigned short integers are 16 bits wide and unassigned long integers are 32 bits wide. This means that when we calculate the product, we don't have to worry about overflow. While this code works, it's not very efficient. The number of times we go through the loop is dependent on b, and since b is an unsigned value, we could end up going through this loop over 65,000 times. Let's look at a different way of multiplying using 14 times 13. We're going to make a table with two columns. The entries in the first row are just the numbers 14 and 13. To create the next row, we're going to double the number in the first column and halve the number in the second column. So the next row of our table contains 28 and 6. We repeat this process until the number in the second column goes to 1. Once we've created this table, we cross out every row which has an even number in the second column. Now we perform one last step. We add all the numbers which remain in the first column. That is, we add 14 plus 56 plus 112 to get a total of 182. Again, if we write this algorithm as a computer program, we might get something like this. What is the maximum number of times we will go through this loop? The maximum number of times through this loop will be less than or equal to the number of bits used to store the value b. Again, assuming that we're dealing with 16-bit unsigned integer inputs, we will never need to go through this loop more than 16 times. Compare this with the previous version of this function, which may require that we go through the loop more than 65,000 times. This second algorithm is essentially how computers do integer multiplication. They multiply one of the operands by 2, they divide the other operand by 2, and every time the number divided by 2 is an odd number, its partner gets added to the product value. It's not really necessary that we divide b by 2. We can simply examine each of the bits in b one at a time. If the bit is 0, we don't need to do anything. But if bit n of b is 1, then we add a times 2 to the n to the product. The next piece of information we need is what the truth table looks like when we multiply bits. This is pretty straightforward. 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and finally 1 times 1 is 1. This truth table is identical to the truth table for logical AND, where if either input is 0, then the result is 0, and only when both inputs are 1 is the output 1. Now the question becomes, how do we use this to our advantage? Let's take another look at multiplying 14 by 13. Writing these two numbers in binary, we can compute the product like this. Since our multiplicand b is 4 bits wide, we needed to compute 4 partial products, one for each of the bits in b. How can we use logical operations to generate each of the partial products? We can take the nth bit of b, replicate it 4 times so that it's the same width as our multiplicand a, and then logically AND that vector with a to get the partial product. Remember that our bit multiplication table is equivalent to logical AND. For example, the 0th bit of b is 1. Use this expression to create a mask of all 1s. Logically AND this vector with a to get the partial product 1, 1, 1, 0, which is what is shown here. Now look at bit 1 of b. Using this expression, we create a mask of all zeros. As before, we logically AND that vector with 1, 1, 1, 0 to get 0, 0, 0, 0, and again, that matches the second partial product. Finally, we have all the pieces of logic needed to write our first simple version of an 11-bit by 11-bit multiplier. Remember that since we're multiplying two 11-bit numbers, that we need to store the result as a 22-bit number to avoid overflow. This is the first simple version of the multiplication circuit. Note that this version still relies on Verilog to generate the addition logic for us. I chose this approach so that it's easy to see the overall structure of the algorithm. I'm going to make several changes which will eventually create a version where I implement my own addition logic rather than relying on Verilog to do the work for me. If you look at the code closely, you'll see that in the case that B is a vector of all ones, this code needs to perform 11 additions. We don't get these additions for free. The next version of the code will eliminate one of the additions. Here is that version of the code. I got rid of the extra additional operation by choosing the initial value for P in a more intelligent manner. If the least significant bit of B is 1, then P is initialized to A. If the least significant bit of B is 0, then P is initialized to 0. In either case, P is initialized to the first partial product. Note that now the initial value of I in the for loop is 1 rather than 0. This is where the extra unnecessary addition operation is trimmed. Again, we didn't get to trim the addition for free. We paid for it with conditional logic. Instead of using conditional logic, we could use a mask to compute the partial product as was done here. The code explicitly calculates the first partial product of the vector A times the least significant bit of B, that is B0, and stores the partial product as the initial value of P. Now look at the body of the for loop. The if statement is gone. We no longer need it because each time we pass through the loop, we explicitly calculate the ith partial product, shift the partial product left I bits, and add it to the current value of P. Now things become a bit more subtle. Every time we pass through the loop, we're doing a 22-bit addition operation. This really isn't necessary. Each time through the loop, we really only need to add the 11 bits of the partial product to 10 bits for the running total for P, which yields at maximum a 12-bit sum. For a better understanding of this, let's look at how we compute the product manually. The string of 11 Ds represents the first partial product. The string of 11 Es represents the second partial product, etc., through the string of 11 Ns, which represents the 11th partial product. Note how the addition of each new partial product has no effect on the bits to its right. As each partial product is added, the number of bits to its left which it affects is also limited. But first, here is the next version of the code. Before going on with the explanation of how this code works, notice that I changed the Verilog programming style from behavioral to data flow. That is, I replaced the always block with a generate block and no longer declare any of the variables to be of type reg. The Verilog code creates an array of bit vectors RT to hold the running total as we add each successive partial product. Note that because each successive partial product is shifted left relative to the partial products which came before it, and that the least significant bit of the running total won't be changed when we add any of the remaining partial products, I directly store the least significant bit into our final result P rather than store that bit of the sum into the running total. Looking inside the for loop, you can see that as each partial product is added to the running total from the previous step, that the least significant bit of the sum is written directly into our final product value P. Also, when the code adds the very last partial product to the running total, the bits which would normally be stored in the running total instead get directly transferred into a slice of our final result P. This logic is a bit convoluted, so you should replay this portion of the video and study the Verilog until you understand the concept. This principle is going to come up again as I continue to improve the efficiency of the multiplication logic. So understanding the technique now is going to save you future pain. Since you're continuing on, I'm going to assume that you understand how I'm minimizing the number of bits which need to be processed for each partial product. You may be wondering why I wanted to minimize the number of bits each adder needs to sum. The answer is quite simple. The logic for adding each of the individual columns of bits is sequential. When we add the column for the most significant pair of bits, we're not really adding a pair of bits. we're adding 3 bits because we also have to add the carry out bit from the next less significant column. Likewise, I can't add that column of bits until the column to its right is finished and provided its carry out bit, and so on down to the column which contains the least significant pair of bits. Because of the sequential nature of the adder circuit, I want to minimize the number of columns which need to be added. Hopefully, this gives us a little bit more performance. And this brings us to the last version of the Sigmol module, which I'm going to present in this video. This version of Sigmol no longer relies on Verilog to automatically create the logic to perform the additions for each of the partial products. Instead, it uses the module adder to explicitly define how the code performs the addition. The adder module, in turn, uses the versions of the half adder and full adder modules, which were presented earlier in this video. Note that this version of the adder module differs slightly from the version presented earlier. You might want to take some time to study how it's different before moving on. Before ending this video, I'll leave you a small puzzle to consider. This version of the Sigmol module is a completely generic implementation of an unsigned multiply circuit for a pair of input vectors which are nsig plus 1 bits wide. If my goal was to build a generic unsigned multiply circuit, I wouldn't use a parameter nsig, which is 1 less than the actual length of my 2 input vectors. I would probably use a more generic parameter, say n, and the unsigned multiply circuit would multiply 2 vectors which are n bits wide. That is, the parameter would specify the actual length of the bit vectors which are being multiplied. With this in mind, when building a module to multiply the 2 significands, why is it safe to replace the last instantiation of the adder module with this line of code? What advantage does this version of instantiating the adder module have? What implications does this code change have for our testing procedures? I'll cover this in more detail in my next video where I discuss even more ways to accelerate the summation of the partial products. Please share this video with friends and colleagues which might have an interest in this series. Questions and comments are welcome. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.